Okay guys, we're going to have a look at a video, the last video in the AS Chemistry course for mechanisms. All the other videos on AS Chemistry mechanisms are already on the YouTube website. They are the electrophilic addition of a halogen to an alkene, or a hydrogen halide to an alkene, and also the free radical substitution with an alkane. This is the final one that involves nucleophilic substitution this time, and it is with haloalkanes with hydroxide ions in aqueous solution. And that's important when you read the question, that you take a look at the solvent, because those of you who are on the ball will remember, or hopefully know, that, and I'm just going to represent a halogenalkane by R hale, where the R group is a methyl, ethyl, and a alkyl group. You should know that by now. If you did carry that reaction out with a different solvent, so let's say an alcoholic solvent such as ethanolic solvent, you can see I've written there, this time you will get a different product. You will get an alkane, you will get water, and you will get the hydrogen halide, so hydrogen chloride, bromide, etc. So the solvent in this particular reaction is of a great importance. Aqueous solvents give us the alcohol, if you look at this instance, and if we use an alcoholic solvent, you will get an alkene. So it's a completely different organic product. Second thing is, for the reaction of hydroxide ions here in ethanolic solution, you do not have to know the mechanism. Okay, so however, you do need to know the mechanism of hydroxide ions with aqueous solution, which is the one that we're going to cover in this video today. Okay, so just bear that in mind, always read the particular solvent, and we will move into the mechanism. So as I said earlier, this is the general equation, so this is clearly not a mechanism. Okay, this is the general equation of a halogenalkane. Okay, again, R hale with hydroxide ions to give us, in this case, we get an alcohol and we get a hydrogen halide. Well, that'll be determined by the halogenalkane we begin with. Okay, maybe hydrogen chloride, hydrogen bromide, hydrogen iodide, etc. Okay, and all you're doing really, guys, is wherever the halogen is on your parent molecule, you take it off and you replace it with an OH, and then you name that alcohol. So for example, if I started off with a molecule as so, okay, and I reacted it under these conditions with hydroxide ions, I simply remove that and I put it there. Okay. Likewise, if the Cl was there, drawing my product, I put my OH there. Likewise, again, if I had two Cls or two Brs, or okay, both of those will go. Treat them just exactly the same as one, and we will get what we call a diol, a dialcohol. Okay, so when you're writing the equation and drawing the structure of the product, and therefore naming the structure of the product, that, like in much functional group chemistry, you follow that principle. Right, then, so we've talked about this being nucleophilic substitution. Well, hopefully you can see why it's substitution. The halogen is removed, replaced by an OH substitute. The nucleophile, the hydroxide ions act as nucleophiles. Nucleophiles are attracted to areas which are deficient in electrons. So the carbon in the carbon halogen bond is attached to a halogen, of course, which is highly electronegative, and you get an uneven distribution of charge around this bond, where you end up with delta positive carbon and delta negative halogen atom. A nucleophile has a lone pair of electrons on it and a negative charge, or a delta negative charge. It doesn't necessarily have to be negative, okay, so it can be delta negative, and is therefore attracted to this area of denser negative charge. Okay, and that is acting as what we would define as a nucleophile. Okay, so you can hopefully see why hydroxide ions are nucleophiles. They have a negative charge and they have lone pairs of electrons on the hydroxides. Other nucleophiles you might come across would be things like ammonia, okay, which has a delta negative positive charge on it. Cyanide ions will be in the syllabus. Okay, you come across them, and again negative charge. And all of these are things which react with haloalkanes in similar fashions. Right, let's have a look at this mechanism then. So the first thing that you must do when you get the mechanism is you have to look at the haloalkane that is given, and you must decide, is it primary or is it tertiary? The simple reason being that the two different haloalkanes will undergo slightly different mechanisms, and if you draw the wrong mechanism for the wrong haloalkane, you're going to cost yourself a lot of marks in an exam. So that's the first thing you must do, okay? Provided that you have learnt the mechanisms and learnt them well, then if you know them, applying them to the primary or the tertiary should be pretty straightforward. But if you have not made the right decision as to whether it is a primary or a tertiary, then you're going to be in a bit of bother. Right, I'm going to start off with a primary haloalkane, okay, and we'll talk through the mechanism of that, and then we'll look at it at a tertiary. So let's say the question is to draw so we've got to draw a mechanism. Sometimes they call them a flow scheme or a flow diagram, okay, of let's say we have 2 methyl 1 chlorobutane. So we'll make it reasonably challenging to begin with. We don't want to set a really easy one. Now you will be expected probably to have in there your curly arrows, okay, and you'll also be expected probably to have in there relevant dipoles. And relevant dipoles are just ones that are of importance within the mechanism, as opposed to other dipoles which might exist which are of no significance. So the first thing I've got to do is draw this out to decide whether is it primary, is it secondary, or is it tertiary. So there we go, there's my molecule drawn out, and the key carbon that we make our decision based on is the one with the red dot on it. That is attached only to one other carbon or to 2 hydrogens. Therefore, this is a primary one. Some people can be thrown by the presence of this little methyl group here. Okay, that's not on our key carbon here. Okay, so I'm going to draw this out just a little bit bigger so that you guys can see it. So we'll go 1, 2, 3, 4. With CH3 there, or Cl there. We'll put our relevant dipoles on. And these are all hydrogens at the end of these bonds. I'm not going to draw them all in. Okay. And then I draw my hydroxide ion. Okay. Which is here. Okay. Now, it's important that we don't draw a hydroxide ion approaching via this route, this direction, sorry, or this direction. Because the hydroxide ion is negative, as is the chloride, so it would, or the chlorine, and it will just repel it back out again. So when we're doing our curly arrows, and the curly arrows are a really important convention, guys, and we must show them starting from the middle of a lone pair and going towards the delta positive region that they are. So they're really picky, so they go from the electrons starting in the middle of the lone pair to the delta positive carbon. Okay. Now, that will cause the electrons around this carbon to be repelled. The ones that are repelled the most, and I'll just get rid of these red arrows, the ones that are repelled the most will be the ones in the chlorine. Okay, and that causes what we call a transition state. And a transition state is basically, or what it says on the tin, in that it is something that forms between the start and the end of, in this instance, a reaction. So all we've got to do now is redraw our molecule. So I'm going to take this part of the molecule here, guys. I'm just going to condense it down to a C3H7 just to make life a bit easier. There's my delta positive carbon that I had. I'm not going to call it delta positive anymore. Okay, it has on it, it has its 2 hydrogens, which it always had, here and here. Excuse me. It has here a C4H11 group, okay, which is that. I've just condensed that down. And what we're going to show is that the Cl and the OH have not quite joined, nor have they quite left yet. So we represent that by this dashed line. And we have a negative charge to account for here, okay. Now you'll note my delta charges have all gone, okay. And the final step in this is that we have our C4H11. Now this bond does break, and this bond has completely made with my carbon. So I've now got my alcohol, and I need to remember to account for my chloride ion, which is now a completely negative chloride ion. It has taken both the electrons that were in that bond onto itself. So we get a type of bond breaking here. And if you can remember from earlier in the course, that's a type of bond breaking called heterolytic, which gives you ions, as opposed to homolytic, which give us our free radicals. Now there are two steps in this reaction clearly. This one here, the first one, is quite a slow step and it's driven by heat under reflux. Okay, it's also called the RDS, or the rate determining step. This is the step that determines how fast the reaction happens. The second step here is a very fast reaction, or a very fast step. This intermediate does not hang about for long at all. Now, this is an important step because it determines to an extent what we call this mechanism. Now, the mechanism is obviously called nucleophilic substitution, but we also refer to it as S substitution, N nucleophilic 2. And the 2 tells me how many particles are involved in this slow step. And if we look at it, you can see there are 2 particles. There's the hydroxide ion and there is the haloalkane itself. Therefore, the 2 tells us that. And when you're writing an answer in an exam to say what is the name of this mechanism, I would suggest you write nucleophilic substitution brackets SN2. Okay? And really that's the primary one, guys. And all you do is you focus your efforts around this little carbon here, and everything else that is in the molecule you just redraw as you go through. Okay? And then you name your molecule. Don't forget that this comes in this way. Don't forget your delta charges. Don't forget the significance of curly arrows. Remember this one as well, I should have said, starts on the bond because it is the bond where the electrons are. Okay, it does not start on the carbon, which some people will have it. Okay, and it goes towards the chlorine. Don't forget your dashed lines here with your negative charge up here and everything in square brackets. Don't forget that the delta charges here disappear at this point, and that this at the end is a completely negative ion. Okay, those are all areas where students drop marks. Right, we'll have a look at the tertiary mechanism then. Okay, so we'll have to do the same sort of thing. Obviously, we'll take a different molecule this time. Okay, so say we have 2 chloromethyl propane. Okay, so again, the first thing that you got to do is to draw this thing out. Okay, those are all CH3 groups, obviously. Okay, and again, we've got to work out, is this primary or is this tertiary? That's my carbon of importance there, and it's attached to no hydrogens or 3 other carbons. So this time we have a tertiary, so it's going to be a slightly different mechanism. Now, on the last one, the hydroxide ions, okay, came in and attacked this delta positive carbon. But this time my hydroxide ion cannot get to this carbon, because it's surrounded by the chlorine, which is repelling the hydroxide ion away, and the 3 methyl groups. These are the smallest alkyl groups, but they still have significant electron clouds, and they will simply repel the hydroxide away. So the hydroxide cannot attack this carbon here. That is a thing called steric hindrance, and really what that means is that because of the geometry of this molecule, it prevents the reaction from happening. Because of these groups around the little carbon in the middle, the hydroxide simply cannot get to them. So how are we going to break that bond? We've still got to break this bond to get the hydroxide on to get our final alcohol product. Well, again, we've got to heat under reflux. We've got to heat this very intensely, and as so we're breaking strong bonds here. Okay, hence the reason for the heat under reflux, and this is our slow step. Now this causes again heterolytic bond breaking, so that uneven breaking of the bond where both electrons go to that chlorine. We show that again by the curly arrow, showing that the pair of electrons go towards that chlorine. That means that the carbon in the middle, my key carbon here, has lost one of its electrons and is a positive charged carbon atom now, and you should recognize that from earlier in the syllabus as a carbocation. Okay, it is in actual fact a tertiary carbocation, to be more specific about it. And now at this point, my hydroxide ion, which is in the solution, will come into play. Again, we have a negative charge and we have a lone pair on it. And we draw again a curly arrow. And guys, it's important the arrows are curly, not straight. Okay, they mean a different thing if they're straight. Okay, so then our final product is we have our OH, and don't forget to account for your chlorine or bromine or whatever it is that has been kicked out. Now, this is a very fast step. You've got a positive and negative ion attracting each other. This is the slow step. So this time, how many particles do we have in the slow step? Well, we just have the haloalkane itself. So this time we have an Sn1 mechanism. Okay, so again, all you do, guys, is concentrate your efforts around this carbon here, and you draw all the other groups, whatever they are, each time. I'm putting my CH3s there. Each time as you go through the mechanism. Okay, and you've got some new terms. Well, carbocation is not a new term. Your steric hindrance was a new term. Heterolytic again is not a new term. Okay, rate determining step is a new term, and as is nucleophile and nucleophilic. Okay, so hopefully that helps you with your drawing your mechanisms for these particular primary versus tertiary haloalkanes. Don't forget, guys, the most important thing is you've learnt it. The second most important thing is that you draw out the haloalkane or halogenalkanes that they're asking you about the question, and make sure that you draw the right mechanism for the right haloalkane. Okay, hopefully that helps.